Hi everyone, my name is Rafael, and today I will be talking to you about our work on the weak supervision landscape. This is joint work between people at the University of Bristol and University Carlos III of Madrid. In this work, we focus on the case of datasets with imperfect annotations or imperfect labels. This can happen for several reasons and can take various forms. While there exist many such settings in the literature, it is not yet well understood how they relate between them. This can be of great interest for the dataset owner, as weak annotations can be a cheaper alternative to an expensive, perfect annotation process. Our goal is to introduce a framework that can be used for categorizing weak supervision settings. This would allow the annotator to make decisions regarding the annotation process and allow the machine learning practitioner to understand implications of characteristics of a dataset on learning. On this slide, we present an example. We see a toy dataset and 3 instantiations of annotations. In all 3 cases, it is a multi-class classification problem with the 4 classes distinguished by their color. The first case depicts the true labels, which could, for example, be obtained when an expert is handling the annotation process. In the second case, we have what is known as noisy labels. In these settings, labels are flipped with a certain probability. In the last case, we have superset learning, where now every instance can be associated with more than one class, but where the true class is always provided in the set. The last 2 cases imply that the dataset is suboptimal. This might be due to the nature of the task, or it might be due to choices made by the dataset owner. On this slide, we present the framework, its dimensions, and the categories of the dimensions. The dimensions are listed in the second column, while the categories in the first. We break the description of a weak supervision setting into describing 3 objects. The first one is the true label space, which controls the form of the true and unseen labels. The second one is the weak label space, which defines the form of the labels we get to see, the weak labels. The third and last object is the weakening process, which defines the transformation that takes place. As we have discussed before, this framework can be used for describing a dataset and its annotations, but it can also be used for prescribing an annotation process. As we will see, not all the dimensions can be used for prescription, though. We will now look at the categories separately. We first discuss the true label space. We consider 2 dimensions for describing the true label space. First, the number of classes, and second, whether the dataset is multi-label or not. The first one is straightforward and is concerned with how many classes the task involves. For example, it can be binary or multi-class. The second one is concerned with whether every instance is associated with 1 or more classes. For example, in images of people, do we expect every image to contain just 1 face, or do we expect to see more than 1 faces? The true label space is usually defined by the task and its nature. In mathematical terms, we can describe this as follows. In the first case, labels are vectors of dimension k, where k is the number of classes and can only be assigned to one of the k classes. In the second case, while the labels are still binary vectors, we allow for more than one non-zero entry, which corresponds to an instance being associated with more than 1 classes. We now move to the second category of dimensions, the weak label space. The first dimension is concerned with whether there is unlabeled data available. This can be due to instances being difficult to annotate or not being considered at all. The second dimension is about the number of annotators. While we usually assume that datasets are annotated by 1 annotator, this might not be the case in the case of large datasets. And also, we might not be able to assume that the annotators have similar behavior. The third one is about the number of candidate classes annotators can provide. For example, in the case of difficult instance, do we allow the annotators to provide more than 1 guess? Lastly, there is a distinction between binary labels, also called hard labels, and soft labels, where the annotator does not necessarily make an absolute choice between classes, but can rather provide a distribution across the classes. We can now see how these dimensions can be part of a prescription of the annotation process decided by the dataset owner. On this slide, we see an example of an annotation for a single instance. Earlier, we described the true labels as vectors. Now, we describe them as matrices, since we allow for multiple annotators. The gray box in the middle on the slide and the matrix on the right are two different views of the annotation. We have 4 annotators, as illustrated by the 4 blue boxes inside the gray box, and hence a matrix with 4 columns. The annotators can provide an empty set, as shown by the last annotator, which corresponds to the all zero vector. Lastly, annotators can provide more than one candidate classes, as illustrated by the first and third annotators. Soft labels are not discussed on this example for purposes of simplicity. We now discuss the last category, the weakening process. This category has 3 dimensions. So far, we have assumed that every instance is associated with its own annotation. For example, one annotation for every image. This might not always be the case though. For example, we might know that a person's face is present in a video, but we might not know in which particular frame. In this example, we say that the group of instances, the frames, are annotated as a group. This is the dimension of aggregation, which we'll discuss more about later. The second dimension is concerned with whether the annotation errors take place with the same rate across the classes, or whether certain classes are more prone to errors than others. The last dimension is similar to the second one, but this time the question is whether the error rate is uniform across instances or not. We now see pictorially the distinction between aggregate and non-aggregate weak supervision settings. On the left, we have non-aggregate settings, where there is a one-to-one relationship between instances and annotations. On the other hand, on the right-hand side, we have an example of an aggregate setting where a number of instances share the same annotation. Examples of these include multiple instance learning, where the annotation is positive if at least one of the true labels is positive, and negative otherwise. Another example is label proportions, where we only get to observe the proportion of each class in the group. We now see this in mathematical terms. Instead of being provided with instance label pairs, we are provided with a set of instances and their corresponding back assignments. Then, for each of these groups, we are provided with a label corresponding to the whole group, as illustrated by the equation at the bottom. This shows how the label for back J is a function of all the labels whose instances belong to back J. We now look at non-aggregate weak supervision settings. In this case, we can define a probability function, tau, that maps input labels to the probability simplex over the elements of the weak label space. Another important object is the mixing matrix, T, which is a column stochastic matrix. Each column corresponds to one of the true classes and is a probability distribution over the possible labels in the weak label space. In this work, we have introduced a framework that can be used by both dataset owners and practitioners. For the dataset owners, it can be used for navigating the available options when prescribing an annotation process. In the case of machine learning practitioners, it can be used for describing the annotation of a dataset and understanding its implications in learning. Thanks for listening.